inviting me to this wonderful workshop. So it's nice to be here. So today I'd like to talk about some thoughts on concepts of time, and based on these works that I did with Sjinji Mukohyama and John Cash. So first of all, okay, so let me begin with the introduction. So when we talk about the history of the universe, we usually think of a history of dynamics, and so it means that we talk about sequence of configurations parameterized by time. Okay. And so, for example, when we talk about beginning of the universe, it's just beginning. But when we talk about the more fundamental, question like beginning of the geometrical description of the universe, then it starts from the initial singularity, and before that, there is no concept of space. Okay, so space may be imagined. So then, natural question is this one. So how about time? Okay. Can time be imagined? Okay. So this is a question that I would like to ask in this talk. Okay. So let me explain a little bit about what is known about time and dynamics. I think all of you know already know. And so we know that in any differential invariant theory of gravity, Hamiltonian is somehow constrained up to boundary. So the Hamiltonian vanishes. So this means that there is no evolution of quantum space in any differential invariant theory of gravity. Okay. So the standard picture about time is that the dynamics should be encoded as correlations among different kinds of fields. Different kinds of fields. So in this sense, one of the fields among them should play the role of time, okay? At least one, at least locally. Okay? And of course, the time, this kind of field may change from time to time and place to place, but at least one of them should play the role of time. Okay? So, for example, the inflaton during inflation play the role of time, measuring the time remaining before the end of inflation. Okay? So in this sense, only in this sense, the concept of time and dynamics may be imagined. Okay? So I'd like to make this idea a little bit more concrete. This is the subject of this talk. Okay? The basic idea consists of two concepts. Okay? First one is the clock field. So let me begin with explaining this. So clock field is a field playing the role of time in this sense. Okay? By definition, it must carry at least one number because time is one number, at least locally. And the simplest one is scalar field. So let's consider scalar field as a model of clock field. Okay? And also, I want to recover time translation symmetry after emergence of time, at least locally. So as a symmetry, I'd like to demand that the theory is invariant and shift symmetry. Okay? Phi can be shifted to phi plus constant.
Sjinji, what?
Yes.
In our expanding universe, we don't have time translation symmetry.
Right. Yes.
So that seems like a big assumption if you stick in.
Yes, at least locally. So if we consider time scale and the length scale, which is relevant for our experiment, for example, laboratory experiment, then yeah. So we don't. So the time scale associated with cosmological expansion is very very long. So in this sense, I'd like to assume this transition symmetry as approximate symmetry, at least in our laboratory. Oh, by the way, if you have any questions or comments or criticism, please stop me at any time, as always. And so also I want to recover. This is also this also approximate symmetry in the sense that I explained. So that I want to recover the time reflection symmetry at least locally in space and time. Okay. So that I want to recover this so that I demand that the theory is invariant at this symmetry. Okay, phi goes to minus phi. Okay. So and of course the clock field does not have to be the same everywhere every time. So we can consider multi-clock fields, multi-clock models. But for simplicity, let's consider just the simplest case, namely the single clock model in this talk. Okay. So for example, if we have confusion for clock field like this, and this is the contour of clock field, then for example, in this region, the time flows here to there. Okay. And in this region, the time flows from here to there, and from here to there. So depending on where you are, the time may flow in a different direction. But if this region is large enough in this direction and this direction, then we can accommodate our universe in space and time. Okay. This is the idea of clock field. The second concept in our idea is effective metric. So let me remind you this idea of emergent Lorentz symmetry. So the Lorentz symmetry, we know that it is a very good symmetry in our nature. But it does not have to be the fundamental symmetry theory. It could be accidental symmetry emerging only at low energy. Okay. This is the idea elaborated by these people. So if this is the case, then how about Lorentz signature? Okay. Can this Lorentz signature be emergent? So let's suppose, in order to answer this question, at least in order to think about this question, let's suppose that there is no concept of time at the fundamental level, and let's start with the four-dimensional Riemannian metric, okay? Namely locally Euclidean with signature plus plus plus, no minus sign. And then the idea about effective metric is that physical fields like electron or positron or Higgs field and so on may couple to not only to this fundamental metric but also the clock field. So that the effective metric, which is composed of these ingredients, this metric and the clock field, may be different from the original. Okay. The question is, can this effective metric have a signature minus plus plus? Okay. So this is a question that I would like to ask in this talk. Okay. Any questions so far?
Can you specify what you mean by the notion?
Yes, that is what I would like to explain. Any other questions or comments? Yes.
So, what's going on with causality in this level? If you have a causal, I mean,
Right.
before going
There is no concept of causality at the fundamental level. But my proposal is that time and dynamics and causality, those things are emerging at low energy. To be precise, at long distance, because there is no concept of time, there is no concept of energy. So at long distance, those concepts emerging, and at least locally, we cannot see that the fundamental theory is Euclidean. But we are treated in some sense. So this is what I'd like to explain. Yes.
Logically, I would think that there couldn't be a dynamical scenario that takes you from all plus signature to all minus signature just because the character of the differential equations is changing from
Maybe yes.
elliptic to hyperflux.
Right. But yeah. So in this case, just for simplicity, I like to start with all plus to just minus plus 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 for simplicity. But if we consider something like landscape, maybe different landscape with different signature, different dimension could be possible. But that's too much for me, at least now. Okay, maybe later. So let me explain this. Let's explain some simple examples to answer this question first. Okay. So let's consider a scalar field chi in flat space. Okay. So this is different from the scalar field responsible for time, namely clock field. Okay. So this is the kind of matter, model of matter field. Okay. So suppose that the clock field has a non-vanishing derivative and which is almost constant in some region, okay, at least locally. Okay. And let's choose one of the coordinates with t so that t is proportional to phi. Okay. Because this is constant, we can choose one of the coordinates so that it is proportional to the field phi. Okay. At least locally. Okay. So I mean this is not original time. Just one of the spatial coordinates, okay? Because we start with a locally Euclidean space. So now let's consider the Euclidean action given by this. Okay, this is a standard Euclidean kinetic time plus potential and coupling to clock field. Because I demand that there is a shift symmetry, the phi can couple to chi only through derivative. And also I demanded that there is a D2 symmetry, so we have a 2 here. Okay. Then by plugging this to here, we get this action for chi. Here, this effective matrix is given by this, and this 1, 1, 1, 1 comes from this Euclidean metric. But this minus 2 alpha comes from this coupling. Okay. Because I chose t to be proportional to phi, this gives the kinetic, only the tt component of the effective metric. Okay. So we have 1 minus 2 alpha. Okay. So if alpha is large enough, then Lorentz signature emerges. Okay. So the equation motion for chi could be hyperbolic. Okay. So we can repeat the same thing, same procedure for the vector field. Okay. So again, we suppose that the derivative phi is non-zero and almost constant. Then we consider this kind of action for vector field. Okay, this is the standard kinetic term, and this is coupling to clock field. Then we end up with this kind of effective action for vector field. Okay. So again, we have 1, 1, 1 and 1 minus 2 alpha. So if the coupling is large enough, we again have Lorentzian symmetry. We can repeat this to the arithmetic field, but I will explain this. This is obvious. And so now the question is, can we extend this idea to gravity? And also, how to get this kind of effect? This there for derivative of the clock field. Okay? Namely, we need to have a theory describing gravity and the clock field. Okay? So let me explain this.
Yes. So normally you would say calculating a half would be bad because you would go to any limits from.
Right. So I will mention it later.
Okay.
Yes, we need a UV completion. And I will propose one possible UV completion. Okay. So let me explain this very simple model of clock field and gravity. Okay. So as I already explained, we demand that the theory has shift symmetry, at least approximately, and field symmetry. Okay. And then just for simplicity, I like to demand that the number of degree of freedom is minimal. So the equation motion is second order. So these assumptions lead to the kind of Riemannian version of covariant gravity. Then we end up with this kind of action. Here, G is Euclidean, locally Euclidean metric. So the signature is plus, 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 plus. And we have two functions, G4 and K. Okay? And we have one constant, G5. That's it. Now, we can see that by the definition of G4, we can set G5 equals 0. Okay? By the way, this is a Euclidean Einstein tensor. So the divergence of this guy is 0. That's why we can set this to be 0 by the definition. Okay? And then we end up with this. So we have just two functions, G4 and K. Okay? So this is already, so this is simple enough, but still probably too complicated to see how this works. So let me explain a little bit more, even simpler case. Okay. So this is a special case of this kind of action. Okay. So we just have an Einstein-Hewitt action plus coupling to clock field given by the Einstein tensor. Okay. In the ADM gauge, ADM language, we can decompose the metric into this way. And in the unitary gauge, we can choose T is T proportional to phi. Then by plugging this to here, we get this kind of action by using the famous formula. Here we have two combinations, kij minus k squared and three-dimensional curvature. In the Lorentzian case, we have plus and plus here. But in the Euclidean case, we have plus and minus. So that's why we have plus kappa and minus kappa here. But because of this coupling, we have contribution which is positive here and positive here. Okay. So that this and this has a different combination. So as far as this is positive and this is positive, then we can get the effective Lorentzian signature. Okay. Meaning that if alpha is large enough, we have a Lorentzian gravity. So we can extend this kind of analysis, consideration to this more general case. And actually we can get the kind of correspondence between Euclidean action and the Lorentzian action. So this is the exact correspondence. So this is the starting action, and by doing some transformation, we can rewrite this in this way. Here, G is the Lorentzian measure, minus plus plus plus. And the function f and the function p are given by this formula. So this is the exact UL. So what I did here is actually very simple. If I have time, I will explain more detail, but the basic idea is very simple. Okay. So we started with the Riemannian geometry, and we have the Riemannian diffeomorphism. Okay. As we know, diffeomorphism is just a redundancy description, so we can remove it if we want. Okay. So we remove the part of the diffeomorphism. In this case, with the symmetry associated with the reparametrization of time, not the time, one of the coordinates. Okay. By choosing the unitary gauge, this gauge, so on. So the space is Fourier by phi to constant surface. So by removing this redundancy, we just end up with a set of three-dimensional configurations parameterized by phi. Okay. And as I said, diffeo is just a redundancy. We can recover it again, but we can recover diffeo in a way which is convenient for us. Okay. So we can recover diffeo in a way that looks like four-dimensional diffeo. Okay. So we can undo the unitary gauge so that the end point is Lorentzian symmetry, Lorentzian theory. Okay. So we have a Lorentzian diffeomorphism. This is what this correspondence says. This is the details of the correspondence, but I will skip this. Probably it is not interesting point. Okay. So we end up with this relation. Okay. Now I'd like to explain some cosmological solution. Answering Robert's question. Yes.
So how is it that you're going from elliptic equations of motion to
Right.
hyperbolic equations of
Yes,
motion? Just
that depends on the background. So if we choose the right background, then the perturbation around it behaves like follows the hyperbolic equation motion. In a different background, the perturbation follows the elliptic equation motion.
But there should be a background independent statement, but like in GR we have initial value formulation.
Right.
I specify something
Yes.
on an initial surface that
Yes.
is
Right.
well-defined evolution at all times and so on. And that characterization is different for hyperbolic versus
Yes, so that
elliptic.
so what we know about our nature is that we have so the time evolution is well defined, at least for small perturbation. We have small perturbation and some given background. So as far as small perturbation and a good background, is described by hyperbolic equation motion, we are fine. Okay. So, but if we go into UV or global picture, then the things may be different. Yeah. So everything, in this picture, everything may be determined by boundary condition, but we think we are we are described by Lorentzian theory, because our, perturbation, including us, ourselves, follows the hyperbolic equation motion. We cannot distinguish.
So if this picture were correct, if you did a sufficiently large perturbation in this universe, you'd suddenly
Maybe.
realize that
Yeah.
it's determined.
Right. That's the picture.
But dynamically, I mean, you don't get a singularity. I mean, as I was saying, I mean, when you pass from, let's say, the hyperbolic to elliptic,
Right.
or
Yeah.
or the opposite. I mean, I mean, dynamically, I'm really expecting something really bad to happen.
Yeah. Yes and no. So if we are within this theory, then you are right, because this is just the second. I mean, this equation motion is second order. If the coefficient of the highest order term vanishes, then theory is infinitely strongly coupled, and we can describe it. So that at that point or near that region, the higher derivative terms become important. And later I will propose the possibly UV complete theory
I see.
that could describe everything. Possibly. I don't know. I wouldn't say too much, but good. So any other questions? Okay. Let me explain the cosmology. So probably this answers Robert's question, at least partially. So we started with this theory. So because they are the exact correspondence. So depending on the background, even this theory can describe the Euclidean theory. So the perturbation around some given background may follow the elliptic equation. So in other background, the perturbation may follow the hyperbolic equation. Okay. So we need to look at the background. Okay. So let's consider the cosmological background. Okay. So let's choose flat Friedman background for simplicity. So max is said to be 1, and the shift is 0, and the spatial metric is given by flat space times scale factor. Okay. And the clock field is time function of time. Okay. The equation motion phi, is basically the conservation equation for shift charge, because we have shift symmetry. There is a conserved charge associated with that. Okay. So it is given by this. So this conserved charge is proportional to 8 minus 3. And so this goes to 0. Where J phi is explicitly given by this formula if we use this parameterization. Then the metric equation motion gives us kind of Friedman equation. Where M effective is given by this. Okay. And so if we consider P prime and F prime near local minimum of P, then they behave like this. So the right hand side looks like the dark matter plus dark energy. because the J approach to 0, so they are the kind of attractor. Attractor is projector, and so that's why we have kind of dark energy. And how it approaches looks like that. Because of this behavior. Now, we need to see whether perturbation behaves in a good way. Okay.
Sorry, you went too quick. Can you explain again where the dark energy term came from? That was a P0?
Yes. So dark energy could be basically the value of P0 at the local minimum. Oh, minus P. So this is like
I guess I missed what P0 is.
Okay, sorry. Yeah, P0 is a value of function P at the local minimum.
Isn't this very similar to the Gauss condensate?
Similar, yes, and also similar to K-sense, yes. So if we consider K-sense like or Gauss condensate, then the P, at the minimum of the P, the value of P times -1 play the role of Cosmological constant. And how it approaches to this minimum corresponds to this dark matter. Something like that matter. I wouldn't claim that this is dark matter in our universe, but looks like that. Does this answer your question?
Can you go back a slide again?
Yes. Yeah?
So P is a function of the kinetic term, right?
That's right, yes.
So for P to have a non-trivial value, it means that the gradient of the scalar is non-vanishing.
That's right.
So
That's what we want. Exactly.
yeah. So does that imply some sort of violation of part of Lorentz symmetry?
That's right. So exactly. So yeah. In some sense that. So we started with the Riemannian theory. I mean, we have a Riemannian diffeomorphism,
Yeah.
and we break it,
Yeah, of course.
and we recover it
Yeah. So
by introducing surgical field.
the point is that if on the minimum you're actually violating that, right? So my question is really how much can you afford of that without having any problem with observation?
It depends on how it couples to matter field, and we definitely need a coupling to matter field in order to recover Lorentz symmetry, Lorentz signature. And so, of course, we need to fine tune. I will discuss later. Yes,
sure.
but this is a question of the emergence of Lorentz symmetry. Probably some of you will talk about that in this conference. Okay. So yes. So we have some good background. So we need to think about perturbation in order to see whether perturbation follows the hyperbolic equation motion or elliptic equation motion. So let's consider at first tensor perturbation. Okay. So tensor perturbation is included here, and the quadratic action for in Fourier space is given by this. So as far as these two coefficients are positive, we are okay. So the tensor mode follows the hyperbolic equation motion. If not, it's a okay, so F0 must be positive. This is stability condition. In other words, the hyperbolic, conditions under which the tensor mode follows hyperbolic equation motion. In other words, emergence of time. If we consider scalar perturbation, then we also, this is a bit complicated, but we have perturbation of lattice function and shift vector and curvature perturbation. Then after integrating out these non-dimensional degree of freedom, we get action for theta, okay, in Fourier space. This is given by this. This is a bit complicated, but we can work out. And as far as these two coefficients are positive, we are okay. So scalar perturbation also follows hyperbolic equation motion. So we have good background and perturbation behaves in a hyperbolic, follows hyperbolic equation motion. And but as someone already asked, what happens at the boundary between, for example, between Lorentzian region and Euclidean region? The coefficient, we have infinitely strongly coupled. We need a UV completion. So let me explain. Propose a simple, possible UV completion of this kind of theory.
Numerically, just what is the scale of the strong coupling? Just roughly, what kind of scale you?
Yeah. So if we go from the Lorentzian to Euclidean, then there is always point where there is coefficient. The kinetic term vanishes, so that it's infinitely strongly coupled. So the cutoff is zero. Okay. So we need to include higher derivative.
Okay, so it's
however, though, the energy scale is not energy scale, but momentum scale is. So here I'd like to consider power counting linear theory of clock field and gravity. So as before, the theory is Riemannian, and we demand shift symmetry and Z2 symmetry. And also, on top of this, I demand that the theory is parity invariant, because after going to Lorentzian signature, we want to recover probably CPT symmetry. So, because Lorentz symmetry is good symmetry, but CPT is even better symmetry, and the constraint is much stronger. Okay, so we better recover CPT in automatic way. So for this reason, I demand that the theory is invariant under this parity invariance, parity symmetry. And also, it would be nice if we can find the power counting binomial theory, because this has a good chance to be binomial and it will be. Okay. And also this theory must be reduced to a special case of this shift and Z2 symmetric coherentalism in the area, like this. So let me construct this kind of theory. At high energy, at a short distance, so we need to have a fourth derivative. Here we have a four-dimensional diffusion, and so space and for all four coordinates are treated in the same way. And in order to have renormalizability, we need four derivatives. So we have the curvature square term here and there, and also this xe is defined here, but previously I defined somewhere. Sorry. Not here, sorry. I have to go back. Yeah, here. So this is a standard cubic term. So x already has two derivatives. So this also has a four derivatives because curvature has two derivatives. So this also has the answer. So these h terms are all we have if we include just the term with four derivatives. Okay. And but at long distance, we need to include terms with fewer derivatives, these three terms. Okay. And then we end up with 11 terms. That's all. There are no other terms. And also, we can set C5 equals 0 and C6 to be 1 by integration by paths and rescaling of phi and so on. So we have just 9 terms. And by using the notations used in the literature, we have this kind of action. Anyway, what is important is that we have finite number of coupling constants. And this is power counting anomaly. So this is the theory that may describe the short distance behavior of this kind of scenario. And actually, this theory is indeed renormalizable, as shown by these people. And at the time when I proposed this was just a power counting renormalizable, but I think that this is indeed renormalizable. But RG flow has not yet been studied, so the question is, does it flow to Lorentzian signature in either? We don't know. Yeah. But what we know for sure is that higher derivative terms become important in the UV. For example, near the boundary of a Lorentzian region, and the physics is purely Euclidean. I think matter action also needs to be being completed by Euclidean higher derivative terms. And I think we don't know this question, but Euclidean quantization needs to be developed based on this kind of action. And so there are many things to be developed. But at least we have a theory which may describe the short distance behavior in this kind of theory.
Actually, a question about this renormalizability. In 77, Stellar has shown that R-squared gravity is renormalizable, so it's kind of expected. But how do you cure the problem of equality?
Yeah, we are Euclidean. Euclidean, so we don't care.
But that doesn't cure it because you still need.
But I'm trying to defend inequality.
Yeah, it's not so much because of the problem.
Yeah, so that's related to this question. I mean, how to quantize.
Yeah.
Yeah.
I mean, it's,
so I don't have the answer. But if we can somehow, quantize the system in a purely Euclidean way, and and the Lorentz signature emerges only at long distance, then this may be a possibility.
And how do you
sounds crazy, but
how do you define unitarity? It's unitary with respect to both.
I don't know. I don't know how to quantize without time yet. So, but at least as far as the action is bounded from below, probably the path integral quantization may be possible. I don't know. And some people, so as far as, for example, before this, just without terms with scalar field, as you mentioned, the theory is known to be renormality, but there's a problem of course if you go to the Lorentz signature. In the Euclidean theory, there is no problem, but I mean, the problem is how to interpret it. And this kind of scenario may give us a chance to think about interpretation. That's my point.
So what's happening with the extra degrees of freedom?
Which one? I mean, scalar field?
In the quadratic gravities, there would be two tensor modes for instance.
Oh, I see. Yeah. So right. So at low energy, I mean, we don't care. Right?
Yeah, in what sense are you?
Not the low energy. At long distance.
But at what sense? Because both of those tensor modes are massless. That would be, I guess I just take
No.
quadratic
I
gravity.
think so. I don't think so.
No.
In the study itself,
Yeah.
one was massive.
Massive.
One of them has a mass that's like cosmological mass.
So I mean, by long distance, I mean longer than the inverse of mass, of course. Yeah. That's what I mean. Okay. So let me quickly go through some consideration about terminology. So we have many free functions and parameters. So in gravity sector we have two functions, K4, G4 and K, or F and P. And also in the matter sector, in the simplest case, we have two coupling constants in each action for each matter. And also we have configuration for the clock field. Okay. The stability of clock field and gravity sector require these four conditions. And we had, in the cosmological solution, we had a kind of dark energy and dark matter. And so this dark energy should be like this. And this part plays a role of a kind of dark matter. But I wouldn't claim that this is responsible for all dark matter in our universe. So this must be smaller than the amount of dark matter. And also the stability of matter sector requires this kind of condition, as we already saw. And also in order to recover the Lorentz symmetry, we need to make sure that the speed limits in matter sector agree for all species. So this kind of almost equality should be realized, probably as a result of renormalization flow, like RG flow. And also so if we have speed of propagation for gravitational waves and speed of propagation of light, they could be different. And we need to know that this is smaller than this one. Okay? If the gravitational wave is faster than speed of light, it's okay. But if it is slower, then there is a chain population for gravitational waves, and there is a strong constant. So let me summarize my talk. I'm running. Okay. So the Lorentz dynamics can emerge as an effective property of a fundamentally Riemannian theory. And this requires introduction of field playing the role of time, which we call clock field. This idea was applied to scalar, vector, and spinor field. I didn't have time to explain this, but we can construct Dirac and Weyl and Weyl and spinor, and construct a standard model if you want. And gravity, as explicit example. In our simple regularization, the clock field is described by the Riemannian version of shift and deep symmetry covariant parallel. And we obtained the dictionary between Lorentzian theory and the Euclidean theory. And we propose the power counting Riemannian theory as a candidate theory. And actually, this is Riemannian theory. And we found the Friedman solution and analyzed the stability of scalar and tensor perturbation. There are many things to do. First of all, we need to develop quantum theory. The title, as the title of this talk says, this is purely classical. So we need to quantize, including time. Okay. And so as I explained, as briefly mentioned, we can construct this spinor field. But so far, we didn't succeed to have for them in parity invariant. So this is not explicitly CPT invariant automatically. So this kind of construction is needed.
Okay.
Also, we need to understand black hole and singularities. And what is interesting is that we maybe embed the Lorentzian ds CFT inside Euclidean ADS CFT. Because going from Euclidean to Lorentzian, what was ADS becomes Nordita. So the well-formulated Euclidean ADS CFT could be interpreted as less understood Lorentzian ADS CFT in this correspondence. And also the emergence of Lorentz symmetry and low energy must be understood. And more speculatively, so multi-scope models may be developed, and if we combine this idea with compactation, maybe we may have landscape with various signatures and dimensions. This may be too crazy, but maybe some possibility. Thank you very much.